Welcome to this talk on KnitGIST, a programming synthesis toolkit for generating functional machine-knitted textures. I'm Megan Hofmann, and my co-authors are Jennifer Mankoff and Scott Hudson. We contribute to the burgeoning field of algorithmic machine knitting, which is largely based on the work of McKenna et al. Presented at SIGCHI 2016, where they developed a compiler for a machine-level language for operating industrial knitting machines like the one pictured here. This is the basis and can be combined in higher-level programming languages such as those presented by Casper et al. And myself, Hofmann et al. At UIST 2019. This serves as the backend to this work. Past research is largely focused on creating knitted shapes, such as being able to render a Stanford bunny using knitting, or to create soft actuated objects like this lamp. But we contribute to the area of knit textures, which can determine the mechanical and aesthetic properties of knit fabrics. Knit textures can curl up on themselves, or shrink and stretch in horizontal and vertical directions. And these textures can be created using KnitSpeak, a programming language for knitted textures based off of hand knitting instructions like those shown here. This presents us an opportunity to generate complex textures tailored to a designer's purpose, such as designing swatches with target physical properties, creating hand-knit patterns with target aesthetic properties, or combining each of these different properties to create functional and attractive objects. This work builds on the stochastic program optimization technique defined by SIGCHI et al., which is a super-optimization programming synthesis technique that searches a space of non-looped programs, such as KnitSpeak, and is effective in non-convex, discrete search spaces. We present KnitGIST, a generative instantiation synthesis toolkit for knitting, which produces complex textures based off higher-level goals defined by a programmer. It applies concepts from program synthesis and uses an extensible API, which is amenable to a variety of domains. The framework can implement a range of optimization techniques, such as hill climbing methodologies and genetic algorithms, by mixing and matching structures from our extensible library. It's currently a programming interface, but it is structured to support constructing interactive tools in future work. For the rest of this talk, we'll present an overview of the framework and the optimization loop at its center. We'll follow this up with a description of heuristic maps, which are the core contribution of this work. Heuristic maps are composed of objectives and tactics, which we will then provide examples of how those are implemented. Finally, we'll provide a demonstration of how you might program a heuristic map in order to create a higher-level object. The KnitGIST framework consists of a library of synthesizers, objectives, and tactics, are combined by the programmer in a weighted mapping to create a heuristic map, and the synthesizers generate random textures based off of width and height parameters defined by the programmer. We start the loop with the n-best population of textures generated randomly by the synthesizer. We score each of the candidates by their objectives, and then select a candidate with a bias towards the one that is currently performing the best. This is to ensure that we don't necessarily jump into local maxima with each iteration. If that candidate meets the programmer's requirements, then we're done and we can move on and knit our object. Otherwise, we choose a tactic that will modify the texture in a small way and then apply that tactic to the candidate texture. This will create a new texture, which we then feed into the population. The objective function is defined by a heuristic map, which is a weighted mapping of objectives which measure how well a given texture performs on a given metric, to tactics, which are small operations on a texture which produce a new texture. Objectives are weighted based off their value to the designer. So in this scenario, the objective 3 style is weighted more highly than the objectives of symmetry and curl. Tactics are weighted by how likely they are to improve a given objective score. So in this scenario, the mirror stitch tactic is more likely to improve the curl objective than the flip stitch tactic. You can map tactics to multiple objectives. Notationally, a heuristic map is defined by a set of objectives, O, each of which has a score, S of O, that is between 0 and 1 on a given texture, 1 being matching the objective and 0 being not matching the objective. Each objective has a weight defined by the programmer, beta of O, and we also have a set of tactics, T, and a weighting alpha of O to T, which is between each objective and its tactics. In order to select tactics, we first have an objective function, f of O, which is simply a weighted sum of the weights of each objective times its score. We define the value of a tactic for improving an objective as the proportion of the weight of that objective to that tactic over the sum of all of the weights of that objective to any tactic. We also define the importance of improving any particular objective as the weight of that objective modified by the difference between 1, the maximum score, and the current score, divided by the sum of all of the weights of any particular objective times its score. We combine these values to create an expected improvement score, or an EIS score, for any particular tactic over the whole set of objectives. This is simply the sum for every objective of the value of the tactic times the importance of the objective. Conceptually, a greater EIS score implies a tactic is more likely to greatly improve the objective function. We select tactics with a bias towards the have the greater EIS scores, but leave some small probability of selecting a low-value tactic, which widens our search space. In order to create these heuristic maps, we provide an extensible KnitGIST objective library, which consists of functional objectives and aesthetic objectives. The functional objectives are curl, shrinkage, stretch, and opacity, and the aesthetic objectives are style, symmetry, and imagery. For the rest of this talk, I will describe the curl and style objectives. But first, a brief introduction to knitting. Consider a yellow loop of yarn. If you were to pull on either end of the yarn, the loop would unravel. But if we pull the yellow loop through a green loop and pull on either ends of the green loop, then the green loop will not unravel. In this scenario, the green loop is a parent loop to the yellow loop, which is a child. We can pull a loop from back to front, which creates a knit stitch, or we can pull a loop from front to back, which creates a purl stitch, each of which have an intrinsic positive or negative curl. And if we align these stitches across an entire piece of fabric, we can create a texture that curls on itself or shrinks and stretches horizontally, as in these photos. We can decrease and increase the number of loops we're working with by pulling multiple loops through each other or adding a new loop onto the set. And when we do this, it creates small eyelets in the fabric which are used to create lace patterns. We can cross stitches over one another, which across a whole fabric creates this winding pattern called a cable. Given this information, we can estimate the curl of a single loop, L, presented in yellow, based off of its parent loops, P, which are presented in green. The orientation between the loops is defined as -1 if they are front to back and 1 if they are back to front, because loops pulled front to back curl backwards and loops pulled back to front curl forward. The curl of a loop is just the average of its orientation with each of its parents. But we must also consider the effect of child loops, M, presented in red, on the fabric. And so the curl of a loop L is also defined with a recursive operation of the curl of its child divided by a decay factor. And if we want to estimate the curl across a whole texture, we simply take the average curl of all of the loops on the bottom row. Knitters tend to classify textures into knit purl patterns, lace patterns, and cabled patterns. So we took a sample of over 1,500 textures from an online database of knitting patterns, hand-categorized them based off of their swatch photos, and tokenized them to determine what stitches were used. Using a C4.5 decision tree algorithm, we were able to get an accuracy of 95.6 with a kappa value of 0.86. We also provide an extensible library of tactics which slightly modify a texture to create a new texture. We have flip stitch orientation tactics, lean stitch left and right tactics, replace stitches, mirror stitches on the axis of symmetry, and swap stitches between two textures. For the rest of this talk, I will present the flip and lean operations. A flip stitch simply means to take a stitch that is pulled through back to front and flip it to be front to back. We can also lean stitches, such as decreases, which tend to lean left to right, or lean cable stitches, which tend to be crossed over in a left to right pattern. In the paper, we present 3 demonstrations for forming heuristic maps to create a variety of physical textures with physical and aesthetic properties. For the rest of this talk, I will focus on the final one, a lampshade. So if we want to create a lampshade, we might consider a series of objectives. First, we want it to curl up on itself on the top and bottom regions so that it can grip the lampshade. We also want to make sure that it has low opacity stripes, which allow a little bit of light through. And we want to maximize the elasticity of the fabric so that it can wrap around the frame. Additionally, we might add cabled stripes to add a little bit more complexity to the texture. Using domain knowledge from knitting, we know that we can use the flip stitch orientation tactic to affect the curl and max elasticity objectives, because this will align the stitches. And we can add in increases and decreases to create eyelets, which create a lace pattern. Additionally, we can add in cable stitches and a particular type of increase-decrease pair, which appears like a cable, to create a cable pattern. And the resulting lamp has gray edges that curl in and cling to the frame, blue stripes that let light shine through, and green cables that add a nice attractive texture to it. It's worth noting that this is actually a rectangular swatch, but because it is so elastic, it is able to stretch around the conical shade of the lampshade. We also note that this is a hand knit sample, though we could have machine knitted it. Unfortunately, we did not have access to our industrial knitting machine during the COVID-19 pandemic. In summary, programmers can map valuable objectives to tactics, which take small steps through any search space. This is built on top of a heuristic map, which allows us to take small steps with a bias towards improving the texture, but allows us to widely search the space by adding in some randomness. KnitGIST produces textures that match high-level functional and aesthetic goals, and complex heuristic maps can be used to generate functional and attractive whole objects. The system is broken up in such a way that in future work we will be able to create an interactive generative design tool for whole garments. Thank you so much for listening. If you have any questions, feel free to reach out at hoffman.megan@gmail.com.